Welcome back for video 2 on tests of convergence for series. In the previous video, we went through problems 1 and 2 here. We're going to finish off this handout, this topic summary for the remainder of this topic, questions 3 through 5. So question 3 asks for us to show that the series 1 over 2 to the n minus 1, the minus 1 is not in the exponent, converges by two tests, the limit comparison test and the ratio test. So for the limit comparison test, what we are looking for is a few things in the setting. So we want to first record that an is that 1 over 2 to the nth power minus 1, and this has positive terms. And so see that since n goes from 1 to infinity, when n is 1, this is 1 over 2 minus 1, or 1. When n is 2, it's 1 over 4 minus 1, 1 over 8 minus 1, and you can see that the 2 to the n gets larger, and subtracting 1 is never going to make it negative. So that's how you could see that the an has positive terms. Now I am going to choose or define bn to be 1 over 2 to the n. And so I'm choosing that because I can see that it simplifies this ratio. And I know that 2 to the n is a bigger number than 2 to the n minus 1. And so being that I'm dividing by a larger number, I know two things. One is that this bn also has positive terms. And I also know that 1 over 2 to the n will always be a smaller term. So it's important to keep that aspect in mind. Now the next thing that I want to look for is, since this is the limit comparison, I want to know the limit as n goes to infinity of an over bn. So that is 1 over 2 to the n, and let me put the limit back in here. That's 1 over 2 to the n minus 1 over 1 over 2 to the n, which is the limit as n goes to infinity of 2 to the n over 2 to the n minus 1, which if you divide top and bottom by 2 to the n, brings us to 1 over, or limit as n goes to infinity, of 1 over 1 minus 1 over 2 to the n. And the 1 over 2 to the n, as n gets larger and larger, that goes to 0, and we're left with 1 over 1, which is just 1. And so this limit is 1. By the limit comparison test, which says that if the limit is some value that is greater than 0 and finite, then we know that the two series behave in the same way. So here we got 1, which is finite and greater than 0. So now we need to know how the sum of b to the n behaves. Now this is the sum of 1 over 2 to the n, which I am going to rewrite as the sum of 1 times 1/2 to the nth power. And I do that because it makes it easier to recognize that this is a geometric series. Where your common ratio is 1/2. And since that common ratio is between plus and minus 1, this tells us that the sum of Bn converges. So by the limit comparison test, or LCT for short, the sum of An also converges. So that's what we learn from the limit comparison test. Part B gives us a second opportunity to become familiar with the ratio test. So let's go ahead and do that. Remember, the ratio test wants an plus 1 over an. So we've got 1 over 2 to the n plus 1 minus 1 over 1 over 2 to the n, which is 2 to the n over 2 to the n plus 1 minus 1. And I could, let's see, I could multiply. Oh, sorry. There should be a minus 1 here and a minus 1 here. I could multiply the top and bottom by 1 over 2 to the n and see if that happens to give me something more attractive. So multiplying by the equivalent of 1 is a common trick to use, and so this is going to give us 1 minus 1 over 2 to the n divided by, on the bottom we are going to have 2 minus 1 over 2 to the n. Yep, just checking checking that we didn't lose any terms here. Okay, that looks good so far. Right, so from here, we want the limit as n goes to infinity. And the ratio test is looking at the absolute value of an plus 1 over an. There's no negative sign, so this is the limit as n goes to infinity of 1 minus 1 over 2 to the n divided by 2 minus 1 over 2 to the n. And this comes out to 1/2, which is less than 1. And I'm pointing that out because the ratio test says that if it's less than 1, which it is in our case, that we have absolute convergence. So that's what we learned here. So both of these tests show convergence. B is a bit stronger because now we know that it absolutely converges, which, by the way, absolute convergence means that not only does the sum of the absolute values converge, so the sum of the absolute value of an converges, but the sum of an also converges. So I'll make a little note of that here. This implies that both the sum of the absolute value of an and the sum of an converge. So absolute convergence implies that, and the ratio and root tests are strong enough that if you find convergence, you find absolute convergence, which we did here. Let's move on to the next problem, which is number 4. And this one says, explore the convergence of the following series using the alternating series test. And so over here, in the alternating series test, what we're looking at is a few things. We are going to note that based on this form here, our Bn is going to be 1 over n. So alternating series test requires your series to have a particular form, and you're interested in the Bn part, and so Bn is going to be the 1 over n. And we need to check that conditions are satisfied. And so the first condition, which is demonstrating that, let's see, Bn plus 1, that it's decreasing. So we've got 1 over n plus 1 is less than 1 over n. So this is your Bn plus 1 is less than Bn, which means that your next term is less than your current term. And so this does imply decreasing. We also want to check the limit behavior of Bn. And that limit is 0, which is the second thing that we need to satisfy. And so, since we have both of these, that means that the series converges. And that's the beauty of the alternating series test. It's pretty easy once you demonstrate that the criteria are satisfied. All right, so now let's look at the next series here. And so for this one, what do we have? We've got our Bn all right, so we want to put this -1 to the n minus 1 term, which means we had a -1 squared in there, and that is just going to be 1, and then you have n squared over n cubed plus 1, and that, this part is our Bn. This term is just 1. So now we're looking at Bn. So we want to investigate the same criteria that we were looking at before. So Bn plus 1 is going to be n plus 1 squared over n plus 1 cubed plus 1. And Bn is n squared over n cubed plus 1. And so in this case, it's a bit difficult to tell whether the series is decreasing or not. And so it's hard to detect that, at least from trying to use the same approach that we did initially. And so I am going to change tactics, and I am going to let f of x be x squared over x cubed plus 1. And as we did in a previous problem, maybe the previous video, I think it was, I want to look if it's decreasing, then we know that f prime should be negative. So this is low, d high, minus high, d low, over low squared. And let's see what we could simplify here. So I am going to have 2x to the 4th plus 2x minus 3x to the 4th over x cubed plus 1 quantity squared. And that numerator simplifies a little bit more. We're going to have 2x minus an x to the 4th over x cubed plus 1 squared. And so far so good. And so we want to know, when is this going to be negative? Now the denominator is squared, so that's never going to give us a minus sign. So it's only going to be negative when the top is negative. So that's 2x minus x to the fourth, which is x times 2 minus x cubed. I want to know, when is that going to be negative? And so that's going to be negative either when x is negative, or we've got x cubed is greater than 2, or x is greater than the cube root of 2. And so that is what we were looking for. Now x, remember, corresponds to n, and n is a positive counter. And so x being less than 0 is never going to happen, but x can be greater than the cube root of 2. And the cube root, when you go to the nearest integer, corresponds to n being greater than or equal to 2. So now we know that from 2 onwards that the series does decrease. So that's good. Now we have a starting point. And what else? So we've got decreasing, limit. Now we need to look at the limiting behavior as n goes to infinity of bn, which is n squared over n cubed plus 1. And you notice that this is infinity over infinity, so that should make you think of L'Hopital. Which brings us to the next step, which is the limit as n goes to infinity of 2n over 3n squared. And here you've got 2 over 3n, and as n gets larger and larger, you're dividing by a bigger number. The top is staying fixed, and so this is approaching 0. And so we satisfy the 2 criteria that we have. It's decreasing, and that the limit of bn is 0. And so that proves that the series converges. Which brings us to our final example. And this is a test for convergence of the given series here. And for this one, it doesn't specify a particular test to use, but what's bothering me is that the sequence is to the nth power. And so I recognize that, well, if I use the root test, notice the root test is the limit of the nth root of the an part. So nth root is an to the 1 over n power, which is neat because when you have a sequence or a series where the sequence part is to the nth power, the root test is going to remove that n power term. And so that's my indicator of what method to use. So the root test, I want the limit as n goes to infinity of 3n plus 2 over 2n plus 3. This is to the nth power, and this in turn is to the 1 over nth power, which gives me the limit as n goes to infinity of 3n plus 2 over 2n plus 3. And by L'Hopital's, since I have the same polynomial order on top and bottom, this is going to be 3 halves. 3 halves is greater than 1, which means that by the root test, I know that the series diverges. So the root test makes the same decision like the ratio test. So if your limit is finite and less than 1, it absolutely converges. If it's greater than 1, it diverges. If it is 1, then it's inconclusive. You need to find another approach. And that's it. We've practiced all of the different tests for convergence for series, and some you may have preference over others, and sometimes tests require the use of other tests. You might use an integral test showing some, like in the limit comparison test, you might use the integral or the test for divergence to show how one series behaves, and that will give you the decision on the other series. So keep in mind you might actually need to mix 2 or more tests in order to actually finally come to a decision. It's a hard process, but just stick to it and keep practicing.